I just want to say thank you for coming to our first ever Google Tech Talk here at the on this auspicious day when we're packing everything up and moving and stuff. But I just wanted to welcome Paul Hildebrandt up from Denver. He's the president and co-founder of Zometool. And he's going to do some good demonstration for you here and prove to you all of the powers of what? 2, 3, 5, and infinity.
All the way up to infinity.
Yeah, all right. So Paul, take it away.
Great. Yeah, I'm going to try to explain in 45 minutes what I've been trying to figure out for the last 20, 25 years. So if we get partway there, that's good. Anyway, you can help out as we go along. The important thing here is, in order to understand Zome, it helps to be able to jump between dimensions. And that's something we do all the time, right? By seeing. Every time you look at something, you're taking a projection of that three-dimensional object onto your retina, which is a two-dimensional object that's been projected onto a sphere. And so you're actually jumping between 3 dimensions and 2 dimensions all the time. Now in this case, I want to bump it up to 4 dimensions and then maybe even a little bit higher. And if I actually told you right now what I think Zome really is, you'd think I was either really smart or really crazy, and probably the latter. And so I'm not going to say it yet. We're going to go for a little while, because neither of them is really true. Okay, I'm just an artist that kind of got sucked up into this a long time ago, and I've been working on it ever since. In fact, when I was about 17 or 16. Okay, so by way of an introduction to this, I wanted to mention a relationship between 1s and 0s and the numbers 2, 3, and 5, right? Aside from the fact that 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, etc. We go on and on. We'll get to that at the end if we have time to get a little fruity. But my dad had the honor of working with John von Neumann on the first electronic digital computer back in about 1947 in the Princeton IAS project, the Institute for Advanced Studies. And I asked him once, because we sometimes sit up and drink beer, I finally got him to move in with us. He's about 84 years old. And I asked him, what do you think von Neumann thought was the most far-out application of the computer he could possibly come up with, this new wonder toy? And he said, well, I think Johnny probably thought that someday they'd be able to do computer graphics with this, or maybe even predict the weather. Right? So he kind of didn't get things, mundane tasks like word processing or automated accounting, and never even touched upon this kind of information ecology that Google's helping create, right? And that's all what you can do with 1s and 0s. Well, Zome is about what you can do with 2s, 3s, and 5s, and beyond that. And so we're going to start with that. And in Zome, the numbers more tactile. As you recall, when we were in school, we started out, and numbers were these abstract symbols scratched on the chalkboard, right? Which didn't have a whole lot to do with anything, right? And it sort of loses you, right? When in fact, when we're born, we already have an intuitive number sense, right? Because as soon as we crawl out of the womb, what do we see? We see mommy's face. Wow, that's pretty cool. Twofold reflection symmetry. And after that, next thing, it's lunchtime, and we go, what? You mean there are 2 of them? It's a great way to find out about the number 2. So beyond the kind of visual and tactile cues about numbers, we're getting them all the way as we're growing up, right? We're in the car seat, and we go over the railroad tracks. What do you get? Ba-bum, ba-bum, right? There's a number 4, 2 times 2. And we're feeling it, right? Or when our parents read us bedtime stories, we get 1 fish, 2 fish, red fish, blue fish, right? There's 2 cues, right? 2, 2, 2, and 2, right? So what our parents are doing is they're creating kind of a bridge between this intuitive sense of what words mean to this very abstract concept of literacy, right? And that's why reading is so important. I mean, it opens up a whole world to us. But numeracy is completely ignored, right? So we end up with this in first grade. Nobody builds the bridge. We get math anxiety, and the rest is history. And they pass it on. The thing is, most elementary school teachers are women who got math anxiety, got the virus when they were growing up, and they pass it on to all the kids in school, and it follows. I even get spreadsheet anxiety still, right? So anyway, 2, 3, and 5 are represented by, in Zome, the rectangle, the triangle, and the pentagon. Right? It's fairly obvious why the pentagon would be the number 5, right? It's got 5 points, it's got 5 lines, it's got 5-fold symmetry in 5 different directions. It also has reflection symmetry, so the 2 is embedded in there. Likewise with the triangle. Now, I don't know, you might be wondering why didn't we make the third line, the number 2, just a line, right, with 2 points? Well, it's kind of hard to make struts that only have 2 dimensions. So we chose the rectangle, which has 2 times 2 edges, 2 times 2 corners, and they're different, right? And you can see it if you look at the Zome ball really closely. Can you see that? I don't think so. How about this? Right, here's a big Zome ball. You can see that the ball is actually shape-coded. It has the number 2 here, the number 3 here, the number 5 there. Is that fairly clear? I can show you a flattened out ball here if you turn on the projector, right? I can take the ball and I can flatten it out like that, right? And in fact, you can get that very shadow with Zome. Here it is. You can see it, right? And again, you can see here's the number 2, number 3s, number 5s. I mean, the whole thing is made up of those numbers. Those are also the cross sections of the struts. So those 3 things are fairly obvious, 2, 3, and 5. It makes sense that we use those for the cross section of the strut. It also makes sense that you can build a square using the number 2 struts, right? The square has 2-fold symmetry in 2 different directions, right? Actually, it's 2 times 2 points, it's 2 times 2 edges. Everything about the square is similar to the number 4. It's like a 2-dimensional number 4. If I took this in SketchUp and I extruded it, what would I get? Not anyway. The cube, right. And of course, here it is. It's also made up of the blue struts, right? Because it's made up of how many squares? 6 squares, right. Well, 6 is 2 times 3, so you know there's got to be a 3 embedded in there somewhere, right? And most of us don't see that. There's a good reason why we don't see that. It's called gravity, right? The cube is almost always oriented to gravity in space, the z-axis, right? And that's a good thing, right? It's got a nice solid base, and we actually grow up with cubes, right? Our first exposure to cubes for most of us is in kindergarten, playing with blocks, right? And this is a really brilliant mathematical manipulative, just playing with cubes and derivatives of cubes, you know, which include Lego bricks and so forth. The guy that invented kindergarten in the mid-19th century, Friedrich Froebel, had this radical idea that kids were not just small, stupid adults, but that they actually needed to be nurtured. And he used cubes, or these kindergarten blocks, as 4 of the 6 grounding principles for the kindergarten concept. And that really had a radical effect on the 20th century. People like Pablo Picasso, Frank Lloyd Wright, Buckminster Fuller were all graduates of Froebel-style kindergarten. And of course, it also led to Montessori schools and other things like that. But if you're playing with cubes, you're always orienting it to gravity. There it is, flat on the table. And in fact, you know, as adults, we play with cubes too. We build our buildings, we create our cities. Everything is based on that. And pretty much we like to line it up with 3 axes in space, right? X, Y, and Z, or left, right, or, well, you could say east, west, north, south, and up, down, right? And in fact, this cube, because it's so familiar, I'm going to keep returning to it as we go through the talk, because it's sort of a grounding concept. And we can derive everything that I'm going to talk about today from the cube. And another thing to think about is that the cube is what we call a 3-zone zonahedron. And you might see that there might be a relationship between that and the name Zome. It's based on the name was sort of a cross of the word dome and zonahedron. And what that means is, really quickly, here's a star of the thing. It's just Cartesian coordinates. And you can see that all the edges of the cube are going to be parallel with one of those 3 lines. And so that's all it is, right? If I go around here, I've got one zone. If I go around there, you can see these edges are all parallel. That's another zone. And if I go around this way, that's the 3rd zone. That's the z-axis that we always need to respect if we're building compressive buildings on the Earth, because otherwise they'll fall over. So again, the reason that we don't know that there's a number 3 embedded in the cube is because we don't normally stand the cube on its back. If we did, we'd see that there's 3 squares coming together there. And so that's the yellow line. It's got a triangular cross-section right here. Okay? And I could pass them around, you'd be able to feel it. It's also kind of strange, it's twisted in the middle, as is the 5 line. And that's an interesting question, where the odd number's twisted and the even number's straight. That is, the 2 is straight, and the 3 and the 5 are twisted. It has nothing to do with sexual orientation. It's just an interesting question. So if I stick this yellow line into the cube here, and I rotate it 3 times, it lines up with itself, right? Or a better way to see it, if you turn on the light, I'll show you. You can actually project a shadow along that 3-fold axis of symmetry, and so we get a hexagon, right? Which is like 2 times 3 in 2 dimensions. It's a number 6, so 2 times 3 in 2 dimensions. Now, so far what I've shown you is there's a relationship between the shape of the strut, its vector in space, right? That is coming off of here. That's a vector in space. And the number that it represents, but what about the length? If I put this strut in here, you can see the length is right across that diagonal of the cube. I could show with the background there too. If you want, can you see that? It's a body-centered cube diagonal. And go ahead and put that. If you wanted to calculate the length of it, you could take Pythagoras 1 squared plus 1 squared plus 1 squared. Square root of that is root 3 over 2. Which turns out to be cosine 30. 30 goes into 360, right? Because it's 30 degrees is a piece of a circle. 12 times, right? Which is 2 times 2 times 3. That's interesting. Also, you can see really clearly that the length of the yellow line is exactly the height of an equilateral triangle made with these struts. Okay, so there's this intimate relationship between these. Now, in order to understand Zome, we're gonna go to 4 dimensions a couple of times. Actually, with the number 3, the number 4, if you'll accept that the cube is like a 3-dimensional number 4, and with the number 5, where it gets a little interesting. So I'm going to start out with the number 3, because here we have this line segment. 2 points make a line, right? And I'm calling it a 1-dimensional number 3. I'm calling the ball a point. So it's a 0-dimensional number 3. Why? Well, you can call anything. A point could be a projection of anything in the 0 dimensions, right? It could be Einstein's brain. It could be a self-eating watermelon. Anything you want, right? So we can call a point a 0-dimensional 3. Now we all remember that the shortest distance between 2 points is a straight line, right? And I made up these little things this morning. I don't think they may not work, but I've got these 2 points here. And if I had more time, you could see using bubbles, and this is another way actually to figure out the relationship between points in space. Can you see that bubble? Well, maybe I can hold it up against the screen. You can see that the bubble, being very lazy, wants to make a line between the 2 points. You can just sort of see that line, right? So the bubble's telling us that it's the shortest distance between 2 points. Now that's pretty simple, right? We're all nerds, we kind of knew that already. But what about the shortest distance between 3 points? Anybody? A guess? You said I could call on you. Go ahead. What's your name? Let me embarrass you.
Laura.
Laura, okay.
Yeah.
What's the shortest distance between 3 points?
Shortest distance between A and B.
3 points. A, B, and C.
C, yeah.
Right? You got there they are, A, B, and C. You can take the triangle, right? Anything, just throw out an idea.
The shortest distance.
Yeah. Well, how about a triangle, right? Say you're a cable guy, and you need to wire these 3 houses together. And you go, okay, well, I'll just put a line each one. Shortest distance between 2 points is a line, so we got 3 points, we'll just use 3 lines. But of course, your boss comes along and says, what about this, right? You could just have as easily done a V. And the question is there a more elegant solution? And in fact, there is. The bubble knows. And what it is, if I can get rid of that, let's see here. Oops, let me try again. And if you turn on the light, we can show you this. Okay. I'll can you see the solution? And that actually works. It would work with those 3 points, but I'm not going to chance it. So you can see that the real shortest distance between the 3 points is that symbol that's on your hubcap. work this morning. You all drive Mercedes, right? All right, so now we can even do the shortest distance between 4 points because we've got a system, right? Anybody? What's it going to be? What's it going to be? Center point. Okay, it's going to be an x in the square, right? Okay, well, let's try and find out. And again, you could do this with 4 points. It was there all along. I don't know if you can see this, and in fact, there's going to be a line in the middle. But can you see what we're getting here? Yeah. It tricked you, right? It looks like this. I'll hold this one up because it's a lot easier to see, right? And in fact, I mean, you can actually put the x in a box, and you can those are green lines in Zome, and you can measure them, and it's actually longer than these 4 yellow lines and 1 blue line for some reason. And anyway, this is kind of an interesting shape, and we'll get to it later. You might ask me what the shortest distance between 5 points is, since I'm talking about 2, 3, and 5, right? But I'm not going to do it. Instead, I'm going to show you there's a relationship between this and the number 5, and we'll do that later. Okay. Now we need to get up to 4 dimensions real quick. Now, tell me what time it is.
We've gone for 25.
So we're halfway through. Is 45 minutes a fixed deadline?
Okay, I'm excited.
Okay, well, I'll try not to go over, but I'll have to talk fast. All right, so we're getting back to this. We're calling this a 2-dimensional number 3, right? And this would be, or no, 1-dimensional number 3. This would be a 0-dimensional number 3, right? So 1 point, 0 dimensions. 2 points, 1 dimension. How many lines make a triangle? Okay, so 3 lines, 2 dimensions. How many triangles make a tetrahedron? 4. Yeah, tetrahedron means 4 faces. That's pretty easy. Now, for those of you that are not grounded or don't know the tetrahedron, it's really easy to find, right? We'll just take the cube here and we'll put a check mark in every box or a slash across every box in order to connect the corners, and we get this model of the tetrahedron. Now, it's oriented in a way that we're not used to it. It looks, normally, if we orient it to gravity, it looks like this pyramid with a triangle for the base. Okay. All right. So now that we've gotten grounded, now you know the tetrahedron is easy to derive from the cube. We need to go to 4 dimensions. Now we have a pattern here, right? 1 point, 2 points, 1 dimension, 3 lines, 2 dimensions, 4 triangles, 3 dimensions, right? So how many 3-dimensional triangles make a 4-dimensional triangle? 1, 2, 3, 4. 5. You're right. Okay, well, let's do it. And see if we make the bubble. Go ahead and turn on the light. You can see that. Can you see the reflection in that? Yeah, this would be a shadow of a 4-dimensional cube. Now, if it were a regular tetrahedron, a regular 4-dimensional number 3, right? Then all these lines would be the same length, but they've been squashed, right? They've been sort of flattened out. And you can do some other cool things with this. If you want to do deconstructivism, you can make a catenary curve. You can see that of interest to architects, right? That's the best shape for an arc. Or if I knock out another one of these, I get a hyperbolic parabola. You see that beauty? And that would be the universe. Einstein's 4-dimensional universe as worked by time. It's kind of a fun thing. So anyway, we've gone to 4 dimensions. Let me show you once again. Here's another a model of that thing. You can see what we have actually inside here. It is a tetrahedron, a carbon tetrahedron, right? And of course, if you look at diamond, it will take this form. It will actually use those tetrahedra in their most relaxed form. It actually is more difficult to come by, but once it gets there, it's very, very, very stable. It's the hardest natural material on the planet. If it were the normal form of carbon that we see is graphite, which is just made up of hexagons, and they kind of slough off each other, so they're a little bit weaker than the diamond shape. And of course, the carbon actually opens up a whole world of nanotechnology, buckyballs and so forth. And I didn't bring a buckyball today, but you can build one with Zome, and you could do all kinds of weird things. Nanotubes, bucky gears, you name it. It's pretty amazing what you can do with this. And we happen to think that there is a relationship, and that geometry is actually kind of embedded in space, and that's why you can build so many of these things. By the way, Richard Smalley was one of our customers. I don't know if Harry Croto ever got a hold of a Zome kit, but Richard Smalley was the one that discovered Buckminster Fullerene. He said it would be a lot easier if he'd had Zome, because he took a 6-pack of beer and a bunch of paper plates and was cutting things all night trying to figure out what this C60 atom could possibly look like. It's just a bunch of hexagons and pentagons. He probably could have whipped it off in 2 or 3 minutes with Zome. But anyway, where am I? I'd like to get a drink of water, but let's see. I think we can go on to the 3-dimensional, or the 4-dimensional number 4, which is really the cube, because we're still calling the cube a 3-dimensional number 4. And as we already said, the square is a 2-dimensional number 4, so a line segment of length 2 in Zome would be a 1-dimensional number 4, right? Now, I had a thought about this for a second, but it slipped my mind, so we'll get back to it. I guess the idea that you need to know when we're going 4 dimensions with this particular object is the idea of perpendicularity, right? Which we all get because we're all nerds. But the fact of the matter is, anybody that can walk gets perpendicularity, right? Because you can't walk without getting perpendicular. When I do this with kids, I have somebody come up and try to knock me over, and I always kind of right myself because I'm perpendicular to the Earth, or parallel with the force of gravity. So the idea is, if I take a point and I drag it through space for a certain amount of time, say 1 medium blue strut per second, 1/1000, I trace out a 1-dimensional number 4. Let's call it that. Okay. If I drag that through space in a direction perpendicular, I get a 2-dimensional number 4, the cube, right? If I drag that in a direction perpendicular to the other 2, extrude, right? What do we get? The cube, right? And the rest would be left to the reader as an exercise, right? It's obvious how to get to 4 dimensions from there. Should I keep talking about this? Okay, thanks. Because this is really fun. Okay, now, the cool thing is you can do things by analogy. And so if you imagine that I was a 2-dimensional artist living in this plane, go ahead and turn on the light again. I want to work with that. And I said, look, there's this thing called 3 dimensions. And in fact, you can take a square and you can make a 3-dimensional square. It's called a cube, or I'm going to call it a cube. And all you have to do is drag the cube in a direction, or the square in a direction perpendicular to the other 2 directions. You go, well, wait a second, we're stuck in a plane. We can't possibly do that. Right? What if we were just, then I say, okay, let's just try dragging the square in an arbitrary direction. It doesn't really matter, right? We'll just slide it along and we'll trace out a shadow of this 3-dimensional cube. And so that's what we do. We take this and we drag it along these speed lines, and you can see what we get. It traces out this baby, right? Which we can see is pretty similar, right, to the shadow that I'm holding here. But of course, the flatlanders, I mean, you're living in the chalkboard with me right now. You're like, forget that, man. You said that the cube was going to be made up of 6 squares. You can't call that a square, right? There's no way. The thing's too flattened out, right? You can't call that a square. I see those 2, but the rest of them are distorted. Oh yeah, well, that's because of the projection from 3 dimensions down to 2 dimensions, right? So now if we jump back to 3 dimensions, we'll do the same thing, and we'll say, okay, let's just drag the cube through space in a direction that's perpendicular to the other 3. Easy, right? Anybody want to do it for me? Come on. Well, you can't. We ran out of dimensions. What time is it?
You've done 30 minutes.
Oh, I better go. It's over. Well, actually, what if we were to do the same thing? We just drag it through space in an arbitrary direction, see, along those speed lines, and we'll assume that it'll trace out a shadow of a 4-dimensional cube, right? Now, in real life, all these lines would be the same length, and all these cubes would be perpendicular to each other. All the lines would be, right? Here's the star of that. Right now, we've thrown in a 4th dimension, right? These 3 blue lines in space are obviously perpendicular, but this yellow line is also perpendicular. It's just been flattened out when we pressed it into our hyperplane where we're living. Okay. So I can pass that around if you want to see it. Now, of course, the doubting Thomases will say, well, how come you've got all those squashed cubes in there? Well, same thing. It was distorted by perspective. And you can count them. You see those 2 regular cubes. And then there's going to be 6 of these babies that line up with X, Y, and Z in that. These squashed cubes. Okay? Now, was that a convincing argument for the thing? Let's predict how many cubes there really are, right? You got 2 points make a line, 4 lines make a square, 6 squares make a cube. How many cubes make a hypercube? 8. Yeah, 8, of course. I mean, the number pattern works out great. And you can also do it with the number of points, right? In 1 dimension, you have 2 points. In 2 dimensions, you have 2 squared points. In 3 dimensions, you have 3 cubed points, right? So you have 8 points. In 4 dimensions, you have 2 to the 4th, 16. So you can just keep going forever. If you wanted to build a 61-dimensional cube projected into 3 space, you would need, at our current rate of production on a good day, 2 to the 61 balls, which would take us about 731 billion years to make. Now, why in the world would you want to build a 61-dimensional hypercube projected into 3 space? We'll get to that. Okay? Trust me. We don't run out of time. Okay. Now, so far, I've just been talking about the numbers 2 and 3, and they have some pretty neat relationships in space. But 5 is much more cool. Oh, I forgot. I wanted to put the hypercube into a different perspective. Does anybody have a pen light? Well, oh, let's pretend you do. Here, I can do it like this. Go ahead and turn the light on again. I can show you. See that shadow? You could think of that as a perspective shadow of a cube, right? In fact, here it is when it's been completely squashed. In fact, if you're looking down a hallway, then that's what you see, right? And you see that the little squares far away, that's the wall in the back of the hall. The big squares close up, and all these other ones are sort of receding away. Again, doubting Thomases in 2 dimensions, say, well, that, you got to be kidding. That's not a square at all. It's totally distorted, the trapezoid. But we see it all the time. We project 3-dimensional cubes or 3 zonahedra onto our retina, a 2-dimensional surface, all the time when we look around. So now all you have to do is think about having a 4-dimensional eyeball. And of course, I have to do this because I get to do a cool bubble. So here we go. Let's see if I can get it here. Oops, a little bubble in there. Okay. So there it is, right? It's a perspective shadow of a 4-dimensional cube. And of course, the little cube is far away from your 4-dimensional eyeball. The big cube is close up, and all the other ones are receding away. Now that doesn't make sense because the little cube's in the center. But remember, this thing is completely flattened out. I mean, this thing is embedded in the hyperplane of your retina. So it's been completely squashed. And so it doesn't really make sense to say, well, that's in the center, so how can it be the furthest thing away? It's just a projection, it's just a shadow. And likewise, I mean, we saw here, we could do the math again. We've got one little cube in the middle, a big cube on the outside, and then we've got all these squashed cubes, right? There's 3, 4, 5, 6, 7, 8. So it's consistent. We can see there's 8 points in the middle, 8 points on the outside, so it's got 16 vertices. Everything's mathematically consistent. So who knows? Maybe the 4th dimension really exists. In fact, I hope you accept something of existence because we're going to go a lot higher than that. Number 5, okay. Once again, if you want to get to the number 5, let's start with a cube. Do I still have an intact cube? Here it is. Okay. And all you have to do to get to a 3-dimensional number 5 is put a hip roof on it, right? Well, that's, I guess, not all you have to do. Here it is, right? A nice little house. I'm sure this is something we could make in SketchUp, right? Now, if we keep putting roofs on it all the way around, we get this shape. Right? This is a dodecahedron. It just means it's got 12 faces, and each face is a number 5, a 2-dimensional number 5. Right? Remember, we were calling that Zome, the pentagonal strut is a number 5 in space. Now, let's back up. Right? I'm going to say that this pentagon here. Here's a pentagonal strut. It's a 1-dimensional number 5 because I want to prove again, or at least indicate, I can't prove anything, I'm an artist, right? I just see what I see. But this has a length of cosine 18. And so we're calling it a one-dimensional number 5. Cosine 18 is what it's about, well, it's exactly a 20th of a circle, which is 2 times 2 times 5. What do you know? And the height is really cool, too. If I can find a pentagon real quick. Oh, here, we'll just do it like that. You can see that pentagon. You can see it's exactly the height of a pentagon. It's made with the shortest blue struts. So once again, I'm claiming that there's a relationship between the length of the strut, the shape of the strut, and the number it represents. But what about the vector? And here's a cool thing. Somebody just take this red strut and stick it into any one of the red holes. Anyone. It doesn't matter which one. You can put it the inside, the outside of the ball, whatever. And we're going to try casting a shadow with that. And all we have to do is have this parallel with the light rays, perpendicular with the plane, projection plane. Do it. Sorry, there it is. You see what we have there? What's the outside shape? Can you see it? It's got how many sides? 10 sides. It's a decagon, right? Which is what? 2 times 5 in 2 dimensions. So there's a relationship between the vector too. And he really literally could have put this into any one of the holes. And there's 12 to choose from on every ball. So it's 144 holes to choose from. It always works out. So we've got this model. The question is, can we bump it up to 4 dimensions, right? What I'm claiming is that, again, the number 5 strut, the red strut in Zome, is a one-dimensional number 5. The pentagon would be a two-dimensional number 5. Let's hang on over here. Here it is. Two-dimensional number 5. This would be a three-dimensional number 5. Anybody want to try to do the stupid numbers trick here? We're going 2 points to a line, 5 lines to a pentagon, 12 pentagons to a dodecahedron. What's next? What's in 4 dimensions? Yeah, I wouldn't try it either. What it turns out to be is it's 2 times 5 times 12, or 120. So there's 120 dodecahedral cells glued together face to face to make a 4-dimensional pentagon. Yeah, some people are looking over here. I suppose I should hold it up. And it's been creatively named by the mathematicians the 120 cell. Go ahead and turn on the light. Maybe we can make some cool shadows. I don't know. We can see. It's always fun to cast shadows. If I get along the 5-fold axis, can you see that? That's kind of fun. There's a number 5. Again, you can put a red strut in any hole and you get that. I'll lose it. About a number 2. It's much easier to do this with a parallel light source. Like go outside and do it with sunlight, because it really is cool. I mean, there's not, for instance, there's not a square in this whole thing, and yet the squares pop out. Can you see the squares in the corners? Isn't that weird? And then I think I can do a number 3. I should try my luck here. Oh, there it is. There it is. A 3-fold. And can you see how there's 3 all over the place? It kind of reminds you of that shadow of the cube. You know, it hit along the 3-fold axis of symmetry. You've got 6 everywhere, right? Now this is kind of an interesting shape because if you'll notice, it's got a regular dodecahedron, or the 3-dimensional number 5 in the middle. And then as you go out, it gets flatter and flatter. And this can be sort of explained if we take the pentagon and we start to rotate it in space. So why don't we do that? Turn on the light again and I'll show you. So if this is parallel with the viewing screen, then that would be a regular pentagon. If I start rotating it like that, it squashes again. And if I keep going, it flattens out completely in the line segment. Right? And you can actually see that. I mean, here they are. Here's a fat squash, a skinny squash in the line segment. They're actually, it's like they're these hot spots in Zome. So kind of, when I'm rotating this thing, it kind of goes ka-chunk, and it sticks into one. Ka-chunk, it sticks into another, and then ka-chunk, it's flattened out completely. And those show up in this model all over the place. In fact, the whole model is made from those 4 different pentagons, a regular one, and then 2 squashes and a flat one. That works in 3 dimensions as well. If I were to take a regular dodecahedron, here it is. Oh, that's a nice one, huh? We'll get back to that. And I start rotating it in a hyperplane that's different from our own. What happens is it starts getting squashed. It goes chunk, right? There's a squash one. And then it gets squashed a little bit more. That was the fat five-fold one, squashed along a five-fold axis of symmetry. Here's a three-fold one. Here's the skinny five-fold one. Again, right? And then finally, you get this totally flat one, which is really cool. What I do with it? Yeah. Of course, what I did here was I put it. That has the cube in the middle of it, right? So if I, for example, should I hold that up for a little longer? Check it out. Does that look familiar at all? Tell me, what is it? What's familiar about that? Come on.
It's a Honda symbol.
What's that? The Honda symbol. Right, great. Okay, now you're talking about what I drew. Or I guess I'll put it like that. See, now I put the blue line in there, and can you see that?
Yeah.
There's the cube inside the dodecahedron. And now look, it's got that weird shape in the middle, which is what? Remember?
Shortest distance.
See that?
Shortest distance.
The shortest distance between four lines. Now, that, for me, that kind of weirds me out. We're traveling through another dimension, not a dimension of sight or sound, but mind. Next up, the Twilight Zone. That happens. I have those moments with this thing because, it just works that way. It's really weird. There's all these coincidences that are embedded in it. And I think it has to do with those hotspots. Anyway, let me, one other thing. If you check this thing out, I'll go ahead and pass it around because it's a pretty sturdy model. Notice that on the surface, there are all these flattened out dodecahedra. I mean, they're completely flat. All over the place. There's like 30 of them. And that's kind of weird too. But the idea is, as you travel out from that dodecahedron in the center, the things get more and more squashed, right, like this, until they're completely flat on the surface. Because again, it's a projection from 4 dimensions into 3 dimensions, and the hyperplane that this dodecahedron is in is perpendicular to ours. So it's completely flat. Just like when I turned the pentagon around and turned it into a line segment. It's the very same thing. So it works by analogy. Now, of course, I already did bubble models of the cube and the dodecahedron. Those were kind of cool, right? The cube and the tetrahedron, right? The 3-dimensional number, or the 4-dimensional number 3 was this one, or this one, right? The 4-dimensional number 4, if you'll indulge me, would be this one, right? So you want to see the 4-dimensional number 5? Well, you can't, sorry. but it's such a cool bubble, I'll do it anyway. Assuming the gods are with me, because this is a little interesting to me. I'm missing one little bit here. Okay, no. Let's see if I can get this. Like I said, it's a little tricky. Go ahead and turn on the light. Okay, I'm gonna call that good enough. You see it? Maybe a little smaller. Jewel, right? Now this is not the 4-dimensional number 5, but it's related. It actually is the seed from which that will grow, because you're starting out with a regular dodecahedron in the center, and then these squashed ones, 12 of the squashed ones surrounding it. So. And in fact, there's an article in the notices of the AMS, the American Mathematical Society, that shows the whole thing made out of bubbles, because it really is literally can be done as a bubble model. It had to be done with a computer graphic, because I don't know if anybody's good enough with a straw. Okay, how am I doing on time?
It's been 45 minutes.
Oh, okay. Do you want to stop now, or should we?
No, you can go for
Good tenor.
Oh, thank you so much. I'll go fast. Okay, now. One thing about this model, it's got that one cube in it, right? But you can see if I were to take the pentagonal face and I were to draw that line, go ahead and turn the light on again so you can see this better. This is one edge of a cube, right? But guess what? There's 4 other edges. And what that means is there's actually 5 cubes embedded in the dodecahedron. And for those of you that think real estate is expensive, well, that's because we're living in only one of the 5 cubes, right? There's 4 others that we haven't even explored yet. Now, if you were to take the intersection of those 5 cubes, on the inside of that, you would get on the inside of the dodecahedron, you would get this object, which is really cool. I love it because you can make all of its shadows with Zome. Here's one along a two-fold axis. Let me see if I can move this up at the same time. Sorry, I have trouble with that. You see? It's rotating. And what's cool about this is, on this model here, this is made up of diamonds in the divine proportion. I don't know if you remember from Donald Duck in Mathmagic Land when they did this. They said, oh yeah, here's the golden proportion, and they drew the star, and then they draw another one inside, and they say, oh, this was the secret symbol of the, what was it, the Pythagorean Society? And people have been killed for this information being given out. Well, it's pretty cool. I mean, the divine proportion actually determines all the lengths in Zome, right? They're multiplied by those one-dimensional 2, 3, and 5. But anyway, in this case, if you look at this to this, you get the golden proportion. And if you look, and then when it projects down, you get this nutty rectangle in the golden proportion, which is really strange, right? It's like it's going from one set of hotspots in space to another, but it's preserving that divine proportion. Sort of like when we had the cubes in that biggie, right? Or the squares that show up along the two-fold axis of symmetry. It's really weird. Now, if I look at it along a three-fold axis of symmetry, this should be a little familiar. Let's see, where is this? There we go. Kind of looks like the cube that we did before, right? Cube model. And why not, right? Because it's actually 5 cubes. And again, here it is. This is what the shadow, you can build the very same thing with Zome. If you look at it along the number 5, which we'll do here, went right in, you get this really interesting shape, which again, you can see the outside is the decagon, the number 10 in space. And you've got all these interpenetrating stars. So here it is. Now what's cool is if I were to do hidden line removal in that drawing, I would get this guy, which is a Penrose tiling. And this is cool, okay? You know about Roger Penrose? He's this physicist, mathematician, who's been called a 21st century Einstein because he's been doing all this stuff with string theory. 10 dimensions, 11 dimensions maybe? But I digress. Anyway, he came up with the matching rules. Now actually we could call this a Rickard tiling too, but the scientists would get mad at us. Clark Rickard, who's an artist who helped to develop Zome in the 60s, actually came up with the diamonds, and Penrose had a more crude version of what he called kites and darts. But what he did was he came up with matching rules which proved that these things could tile the two-dimensional plane infinitely and never repeat themselves. And that was like, whoa, what's up with that? Well, theoretical physicists grabbed on this and they said, well, maybe it can be done in 3 dimensions. And in fact, it can. And you can tile the plane infinitely with these babies, right? These are squashed cubes and they fit together. If you take actually 10 of each, you can build this guy. And you can actually go forever and it will never repeat itself. Okay, the chemists picked up on this, and this is really nuts. They said, well, hey, you can make crystals like this. And then this guy, Dan Sheckman, who was an Israeli scientist working at the National Institute for Standards of Technology in Gaithersburg, not here, but anyway, he actually discovered them. And he took them into the office of his boss, who went, it's multiple twinning, get out of my office. No way. But actually, it proved to be true, and it actually caused what they say is a Copernican revolution in crystallography, which up to that point had been called a closed discipline. You know, you could not have crystals with 5-fold symmetry, nor could you have crystals that had patterns that would repeat infinitely but never repeat themselves. I mean, they would tile infinitely, but they'd never repeat themselves. So it was a big moment in crystallography when they came up. Of course, all of the quasi-crystal scientists, or many of them, bought Zome kits in a very crude form from us, including Dr. Penrose, and also Linus Pauling right before he died, because he was trying to prove that quasi-crystals don't exist. You know, go figure. But anyway, what I think is really cool about this is you start out with art, right? Here's Clark Rickard playing around with them in the early 60s, making these patterns, right? And then Roger Penrose formalizes the math, and then it goes to the theoretical physicists, then the chemists, and finally, it becomes a reality. Now, what's up with that? It's like we created these things in our minds, and then it was possible to make them for reals. You know, and not only that, but when they started out making them, they were really hard to make. They'd have to take this aluminum manganese alloy, and they would cool it at the rate of millions of degrees per second in order to get these things. And what would happen, I think, is all those, normally when it would crystallize out into a cubic pattern, the atoms have their time to think about it. But if you did it in this really strange thing, they'd have to jump into any one of the 5 cubes. And they would just say, okay, we'll take whatever you can get, because we haven't got any time to think about it. But after a while, they were able to anneal these things for days and still get quasicrystals. And they were showing up all over the planet. Okay, well, now I'm going to get to the really weird part. Okay, this thing could be called a shadow of a 6-dimensional cube. And some of the Russian quasicrystal scientists even proposed that that's what quasicrystals were, that they were some projection from the 6th dimension. Can you see why? Here's the star of it. And it's got 6 lines passing through space. If these were all perpendicular, then it would be 6 dimensions. A guy named Fedorov, a Russian crystallographer, actually said that there's a relationship between an n-zone zonahedron, like this is a 6-zone zonahedron, and an n-dimensional outer shell of a cube shadow. So that's what this is. It's a shadow of a 6-dimensional cube. Now you can go with the yellow lines, there's actually 10 lines in space. With the blue lines, there's 15. If you add them together, you get 31. If you throw in the green lines, you get 61. And this is what I'm saying, that Zome is actually a projection of a 61-dimensional hypercubic lattice in 3 space. So yeah, I told you to leave if I said that first. But that's how those hot spots are created. And that's where you get this amazing number 5. One other thing to note is, remember on this one, you go 2, 5, 12, 120, and then it blows to infinity, right? You can't even get it. There's no such thing as an object with five-fold symmetry in 5 dimensions. It has something to do with the fact that there's no solution to the Penning equation, but don't ask me, I'm not a mathematician. So I was going to do fruits and vegetables real quick, okay? Because what we didn't really get to was the divine proportion. If you look at an apple, for instance, do I might? Let's see if I can do this. Remember Jaime Escalante? Stand at the river. I gotta do that, but see what I got? I get the star in the middle of the apple, right? So it's a 5-fold axis of symmetry, like that. Oh yeah. If you do it with a banana, right? You get a 3-fold, and it's yellow, right? It's even color coded. What's up with that? But what's really cool is when those numbers get together. Remember 0, 1, 1, 2, 3, 5, 8, 13, 21. What are those numbers? Anybody? Fibonacci, right? They show up everywhere in nature. Here is an artichoke. Go ahead and turn the light on so we can see this. An artichoke which has spirals, 8 spirals in one direction, 5 spirals in the other direction, right? Or if you look at a rose, it's got spirals of 3 and 5. Or if you look at the pineapple, it's got, this is really interesting, it's got 13, 21, and 34. Now, what's going on here? Why are they using these numbers? Well, I don't really know, but you can see it everywhere. I mean, when you get done with this, and I'll be done in 3 minutes, okay? Look around at the plants here, and you'll see these spirals everywhere. It's part of nature's design. And in fact, if you go to infinity, at infinity, 2 consecutive numbers in that Fibonacci sequence, the ratio of the 2 of them is what? Anybody? The divine proportion, right? Which is embedded in Zome. It's everywhere. So what I think about, when I think about what nature is doing, I think nature is doing this kind of rational approximation of the divine, right? And it's a ratio of 2 numbers, and it's an approximation of the divine proportion. Now, I'm not talking about creationism or anything like that, but it's also kind of weird. So once again, I'll conclude with that. What I was saying about what you can do with 1s and 0s, right? It's an amazing thing. It's a beautiful creation that we've made, this information economy or ecology, creating access to the masses, to the world's information. It's unbelievable. Well, that's 1s and 0s, and it's a virtual reality that is incredible, and it empowers us in an incredible way. What nature is doing with the numbers 2, 3, and 5 is real virtuosity. And it's been there all along, but it's completely unexplored. I mean, right now, we're about at the same place with understanding this as von Neumann was in 1947, right? I talked a little bit about nanotubes, I talked a little bit about quasicrystals, I talked about how nature manifests these numbers, and yet that's nothing compared to the power of these numbers. Think of it in terms of architecture or superconducting batteries for cars. Any number of applications that are based in the real world, right? I mean, we haven't even begun to explore what you can do with those relationships between those numbers, because what's going on, really, in my opinion, is that these numbers, 2, 3, and 5, are knotted together to form the structure of the universe.
Actually, let me get permission.
The Greeks thought that these 5 platonic solids, I only showed you 3 of them, right? The cube, the tetrahedron, and the dodecahedron, were actually the 5 elements. What, 5? There's earth, air, water, and fire, right? But what about this one? They decided this was the shape of the universe. And Kepler, Johannes Kepler, was so impressed that all of those could be derived from each other, just like I built them up from the cube, that he came up with this kind of 16th century theory of everything, in which the planets, the distance between the planets, were determined by seating these 5 platonic solids in hemispheres, right? And so that was his theory. It was a spectacular failure in history, and he laid the groundwork of modern cosmology by failing so badly, right? Today, there's actually radio telescopy data that shows that the universe may in fact be shaped like a dodecahedron. It's about 18 billion light years across, so don't worry about hitting the border anytime soon. And if you did, it's like a house of mirrors and you pop through and get back on the other side. But anyway, something to think about. Anyway, a Zome thing to think about. Anyway, it was fun. Thanks a lot.